Okay, so we asked, we wanted to find out where ST69 came from. So this study was done for a long time, for about 6 years at these phases. And during this phase, we found 700 E. coli isolates from 1,667 women. We did ERIC PCR in all of these. Okay. Now, if we had to do PFGE in all of these, Amy would still be in Berkeley. Okay, because it takes a long time to do that. But with PCR, ERIC PCR, she was do these rapidly. Okay, and one of the interesting observations we made was, for instance, if you look at the CGA, which is ST69, in the first period, you see, it was responsible for a large proportion of drug-resistant organisms. Next year, it went down, and then period 3 went up again, it went down again. You see this? And this is true with other clones. In the first period, we didn't see any CGH. Then it went up, and it went down again. Okay? So when we talk about the prevalence of drug resistance, it doesn't make sense to talk about increasing or decreasing prevalence without specifying the clonal distribution of your collection, study isolates. Okay? You have to always state what the clonal composition of your drug-resistant organism is, because otherwise one strain can totally bias, right? If this was not there, then the prevalence of transaminase sulfur resistance would have been very low. It was just an accident that we did this study during this period, during the period when there was an epidemic of this clone taking place, right? But if we did this study in another period where there was no epidemic of a clone, maybe the drug resistance prevalence would be low. And this is true with all drug-resistant bacterial infections. Drug resistance is mediated by a limited set of clones. Okay? Not all organisms, not all strains in a given species are likely or have the same probability of becoming resistant. And we don't know why this is the case. Why certain clones are more likely to become resistant than others. We don't know the mechanism. Okay? But that's a fundamental fact in infectious, at least bacterial infectious agents. So for instance, during this whole period of 6 years, there was no evidence of increasing prevalence of drug resistance at the university community. Okay? And then ampicillin resistance decreased significantly during this period, but one clone accounted for 75% of the decrease. Okay? So it wasn't a true decrease. It was just all because of one clone. And 4 largest clone groups, CGA, C, H, and G3, accounted for 41% of UTI cases and 52% of transaminase sulfur resistant UTI. So this is the point that I was making. Only 4 clones were responsible for more than 50% of transaminase sulfur resistant E. coli. And interestingly, no initially pan-susceptible clone of those strains gained resistance during this time. Okay? So transaminase sulfur was being used, and they switched to ciprofloxacin, but we saw no increase in ciprofloxacin resistance. So it's not the clinical use of antibiotics that contribute to spread or increase in prevalence. It's not necessarily. And so there are many other examples of these clonal gram-negative strains that are distributed all over the world. Klebsiella that produce KPC1 and 2. Do you know about this? Have you seen this in your regions? In Brazil, this is one of the biggest problems of causes of hospital infections. Okay, NDM1. You've heard of this. This is the one that they found in India, in Pakistan, and it spread to UK. Okay, by medical tourism. Enterobacteria producing a beta-lactam is called VIM, and then ST131. This is the most common clonal strain of E. coli that's distributed all around the world. And it has all kinds of drug resistances, including extended spectrum beta-lactamase producing strains. And these are the ESBL produced CTX expressing gram-negative bacteria all over the world. And the most common one is what's called CTXN15. Okay, so how do these clones get spread all over the world? Travelers, okay, or food that are globally traded. Okay, globalization of food trade is, at least in my opinion, contributing to the spread of these clones. And these are some examples. So CTXN15 has been found in E. coli from chicken, pork, and cows in Europe. CTXN2 E. coli in chicken in Brazil. And Brazil is the biggest exporter of chicken in the world now. Okay? And so Brazil is exporting CTXM2 genes. CTXM2, E. coli, that's when in Japan imports chicken from Brazil. They used to import chicken from China, but because of the scare of the influenza virus, they stopped importing chicken from China. Now they import chicken from Brazil, and now they're getting CTXM2, which is better than influenza, I think. I'm not sure if it's better than influenza. So in medical school, this is what we're taught, okay? How do drug-resistant pathogens emerge? They say there's overuse of antimicrobial agents in clinical settings. There's selective pressures of antimicrobial drugs that create drug-resistant pathogens. And selected drug-resistant pathogens spread in community and healthcare institutions. But in schools of public health, such as ours, this is what we say. There's overuse of antimicrobial agents in food and in food-animal reservoir. Okay? Selective pressures of antimicrobial agents create drug-resistant pathogens, commensals and saprophytes. Not just pathogens, commensals and saprophytes. Selected drug-resistant microbes are spread by food and person-to-person transmission. And pathogens gain mobile drug resistance genes that enter human community and healthcare institutional settings. Of course, both of these are important. I'm not denying that this is not important. Of course this is important. But we think this is even a greater problem. Much greater than this. Okay? And I'm going to provide you with the evidence. So, we did a study of spinach, drug resistance in spinach. Okay? These are, Brazilians don't like to eat raw spinach, but Americans love to eat raw spinach, especially women. I don't eat raw spinach anymore after this study. So, my students went to the supermarkets in Berkeley, and they bought packaged spinach. And this is what they did. So they found 25 batches of spinach, 12 organic and 13 non-organic. Brazilians are becoming also fond of organic food. Californians, they've been doing this for many, many years. I'm not sure why, but they cultured about 230 bacterial isolates from the spinach wash, and 165 of these we were able to do 16S ribosomal RNA sequencing. Okay? And then about 125 of those we were able to identify through blast search sequences that were 95% identical to what we found in the blast database. So that we consider to belong to the same genus. And then 98%, we use the cutoff of 98% to consider them to belong to the same species. Okay? And then 69 of those we were able to do drug susceptibility testing. So from these 69, we found all these bacterial species. These are all, totally harmless bacteria, right? These are all saprophytes. It's not surprising to find these in the spinach. We eat these all the time. They're good for you. But what was surprising that many of these were multi-drug resistant. 12 were resistant to cefotaxime and cefotaxime, which means that they're ESBL producers. Okay? So we did PCR and then sequence of the PCR product, and we found 100% identical sequence of CTXM15, which is, I said before, was the most common CTXM genes distributed all around the world. This is in your spinach. So Americans are eating CTXM15 every day. Okay? We also found CTXM22 and 55. We found, and that was in the Pseudomonas putida. In Pseudomonas testida, we found another one, another CTXM15 that was 99% identical to the NCBI database. We also found a new sequence called BLA-RAN2. It's a new ESBL gene. This has yet to appear in human pathogens, but it will someday. Okay, so by doing this, we can predict what sort of drug resistance genes will appear in the future. And in that study, we did what's called a food resistomics study, okay, where we want to identify every possible drug resistance gene in a food item. Okay, and this is how we did. So we took the spinach, washed the spinach, then have a pellet, mostly of bacteria. Then we shear the DNA, we extract the total DNA, cut them up, put them into a plasmid, and transfect E. coli with a plasmid library. and then we do the drug susceptibility testing of the E. coli, right, and then we do the sequence of the insert. Okay? And do this very quickly. And we found all kinds of drug resistance here in these E. coli clones, all these drug resistances, okay? And we sequenced the errors. And you can't see from there, but the point that I'm making, I highlighted this and this and these. These are all beta-lactamase genes that have not been seen in human pathogens. Okay? By this study, we're learning that many of these saprophytic organisms have beta-lactamase genes. Okay? There are probably thousands of them. So every time human beings introduce a new antibiotic, okay, or beta-lactam drug, we're going to select for a new beta-lactamase. There are right now more than 1,000 beta-lactamases known in gram-negative organisms that are clinically relevant. Okay? But there are more out there. Okay? So every time we introduce a new beta-lactam drug, we are going to select these new drug resistance genes. Okay? So we can now predict into the future what kind of beta-lactamase genes we will select when we develop a new beta-lactam drug. So this is what we call resistomics, so food. I think this is it.